Hi, I'm Charity, and this is my lab report for Lab 4, which is about bar magnets. The purpose of this lab is to measure and understand the distance dependency of a bar magnet and the magnetic field that it creates. The models and fundamental physics principles that we use include the magnetic field of a dipole along a parallel axis, the magnetic field of a dipole along a perpendicular axis, the magnitude of the magnetic field of a dipole magnet, as well as the natural log of that equation, and then also the magnetic field from any observation location. Our results, we found the value of n to be negative 3.5 and the value of capital K to be negative 15.2. We calculated the magnetic moment of the dipole to be 1.2522, and the system in our experiment is the bar magnet and the phone measuring the magnetic field, while the surroundings are everything else. These were our measurements that for each value of microteslins produced by the magnet, as well as the average distances from the magnet in order to get the magnetic field at that location. These are the rest of our measurements where we did our off-axis field at a 45-degree angle, as well as what the D value was and the net magnetic field. Some of our potential sources of error include failure to cancel out the Earth's magnetic field properly, human errors in moving the phone and measuring the distances, and unintentional but inconsistent placement of the magnet. And then this was our graph yielded from our data, and you can see the straight best fit line between the natural log of the magnetic field and the natural log of the observation location R, and that equation comes out to be negative 3.5x minus 15.2. And this is a picture of our experiment we did with the magnet at one end and the phone sliding along the meter stick. This was the calculation for the dipole moment, where the natural log of k was our intercept, negative 15.2. So then k was e to the negative 15.2, and thus k was 2.5 times 10 to the negative 7. K is equivalent to 2kmm, and thus our magnetic moment, the magnitude was 1.2522. And for the code, this was the results of the computational model. You can see that the magnetic field is the largest along the axis, twice as large as the cyan arrows representing the magnetic field at each location perpendicular to the axis. And then if you look in the top right corner, you can see a very small pink arrow that is representative of the magnetic field at the 45-degree angle, and this is all relatively to scale relative to each other in terms of the arrows. This is all of the code where we have our constants, the measured value of mu, and then our function dipole B that calculates the magnetic field at any location, as well as all the different observation vectors, followed by the calculation for the magnetic field at those places, both the parallel and perpendicular locations, and then also the calculation for the location at 45-degree angle. And some additional questions are: which statements apply? When the magnetometer is far from the magnet, there is a near zero magnetic field in the x direction, and the magnetometer moves closer to the magnet, so the measured x component of the field increases. And the question is, what if you hadn't oriented your experiment to compensate for magnetic north? Our results would have been less accurate and likely smaller than our true measured distances should have been, since the Earth's magnetic field would already have been taken into the solution and we wouldn't have moved the phone as far from the magnet. And then the second one, I would have expected all the measurements to be about half as much as they truly were. Because of the two magnets, the measurement should have been about double the amount that they truly were. Or no, sorry, half as much, because the two magnets being end-to-end meant that the dipole moment vector would be twice as strong, and thus making the magnetic field at every location produced by the two magnets also twice as strong. And in conclusion, we have gained a deeper understanding of the bar magnet, its function as a dipole, and the way the magnitude of the magnetic field of a dipole is dependent on its distance.